Hello and welcome to online lecture number 20, which is the last lecture for Chemistry 112 during the spring semester of 2020. And this very last lesson, we'll finish up chapter 21 by discussing the kinetics of nuclear reactions. So when we talk about kinetics, I call back in chapter 12 of this semester, with chemical reactions, the kinetics describes how fast the reaction goes. And we have various rate laws. We have first order reactions, second order reactions, zero order reactions, and we have various equations that we use that are pertinent to the various types of reactions. For nuclear chemistry though, specifically radioactive decay kinetics, all the kinetics are first order. So we only have the relevant first order equations to worry about when doing these kind of calculations. So for first order kinetics, the relevant equation from the integrated rate law says that the natural log of the amount of the substance you have now, so N sub T, compared to how much you had originally, is equal to negative K times T, where N sub T and N sub 0 are the number of nuclei that are present now at time T versus originally, respectively. And then K, just like with chemical kinetics, is our rate constant. Sometimes it's also called the decay constant. And in our textbook, I believe they used the symbol lambda for that decay constant. So the equation in the textbook may look a little bit different from this one, but practically it has the same applications. One way, as we learned in that chapter, to describe kinetics, certainly by the rate constant, but maybe a more practical way to conceptualize how fast the reaction is going is by its half-life, which is, for a first order reaction, always constant. It never changes, and it's a way of describing how much time is needed to pass for the amount of nuclei to decay to half the original amount. So just like any first order kinetics, we can calculate the half-life or use half-life with this equation, with the half-life equal to 0.693 divided by that rate constant. And with nuclear reactions, these half-lives range from billions of years to tens of nanoseconds. So there's a very, very wide range of half-lives to describe these kinetics. So in other words, some radioactive decay processes are very, very fast, and some are very, 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 very slow. Especially in regards to radiocarbon dating and radiometric dating, carbon-14 is very commonly used. So the half-life of 5,730 years is one of the more important numbers here. Because nuclear decay processes follow first order kinetics and therefore have a constant half-life, one application of that is what's called radiometric dating. And this is a process in which we're able to estimate the age of once living objects, whether they be plant or animal of origin. The idea is if we have an object whose age we're interested in, we're able to measure the current number of nuclei, radioactive nuclei in that object today. And if we're able to estimate how many nuclei there were originally, so for example, if we estimate the number of nuclei originally compared to how much there is today, and if that ratio of N sub T to N sub 0 is 0.125, then we can go back in time and figure out how old this object is, at least estimate how old the object is. So in this very simple example, we know that originally this ratio is 1. After 1 half-life, by definition, that ratio will drop to 1/2. After 2 half-lives, that ratio will drop to 1/2 of 1/2 or 1/4. And then for 3 half-lives, it'll drop to 1/2 of 1/2 of 1/2 or 1/8 or 0.125. So if we're confident in this ratio, then we can estimate that this object is about 3 half-lives old. And the actual age then, of course, depends upon what we're actually measuring. For carbon-14, as we'll get into, the half-life about 5,730 years, 3 half-lives old would be about 16 or 17,000 years old. So radiometric dating is not without its controversy, because we have to remember, as part of that equation, we have to estimate how much of that particular nuclei was present originally. And we can only be as confident in our age as we are confident in that N sub 0 part of our equation. And so one of the more controversial experiments that's been done over the last decades or so is trying to determine the age of the Shroud of Turin. The Shroud of Turin is the burial cloth, the supposed or alleged burial cloth of Christ. So if they determine that the carbon-14 ratio of how much we have now compared to how much we had originally is 0.928, the question is, if that's true, then how old is the Shroud of Turin, given that the half-life of carbon-14 is 5,730 years? So this is information we're given, half-life of carbon-14. This is the current ratio of how much carbon-14 we have now compared to how much there was originally. And then we determine time t. Well, one way to go about doing this is to use the half-life in this equation to calculate this rate constant, or otherwise known as the decay constant. And then once we know the decay constant, we plug in that decay constant into this equation. We know this ratio is 0.928, and then solve for t, as we did back in chapter 12, those applications of chemical kinetics. So if we follow that plan, we first use this equation. From this equation, we'd say that the rate constant is equal to 0.693 divided by the half-life, which is 0.693 divided by 5,730 years. So for carbon-14, its decay constant is 0.693 divided by 5,730, or about 1.209 times 10 to the minus 4 reciprocal years. And we'll kind of say that number because we'll be using that same number again in the next couple examples. So that's our decay constant for carbon-14. We know this ratio, so this says that this equation time t, which we're going to solve for, must be equal to negative the natural log of that ratio divided by our rate constant k. Now we start plugging in our values. So time t is equal to negative the natural log of our given ratio. Remember, time t is only going to be as confident as we are in this ratio, divided by the decay constant. And it gives us then a value of negative natural log of 0.928 divided by 1.209 times 10 to the minus 4, gives us a value of approximately 618, and the units would be years. So if this measurement and these estimations are correct, then this would indicate that the Shroud of Turin is only about 600 years old. And so if that's true, then it couldn't possibly be the burial cloth of Christ, who lived about 2,000 years ago. Then there's another example of the same type of equations. We have a cave painting where we determine the carbon-14 ratio of how much carbon-14 we have now compared to how much there was originally is about 0.157. If it's carbon-14, how old do we think this painting is? So our only thing different is that our ratio, as given to us in the problem, is 0.157. It's still carbon-14, so this number is still correct. That means this rate constant is still correct. So the only thing different is that we have a new ratio. So our time t here equal to negative natural log of this ratio. As time goes on, this ratio is going to be decreasing. So we do expect, if nothing else, that this cave painting is much older than the 600 years old that the Shroud of Turin came to be, divided by the decay constant, years. Then we get our value of negative natural log of 0.157 divided by 1.209 times 10 to the minus 4 gives us an age of about 15,300 years. And finally, our last example is that if we found a meteorite and the meteorite was carbon dated, so we used carbon-14, the ratio of how much carbon-14 there is now compared to how much there was originally, to be 100,000 years old. And the question is then, if that's true, then what percent of the original carbon-14 would still be present? So if in fact this meteorite is as old as it's claimed to be, how much carbon-14 there is now compared to how much there was originally. So let's see, we use the same equations, but just a little bit different application of them. So it's still carbon-14, so still same half-life, same decay constant. Here, though, we're told that the age is 100,000 years, and then we're asked to determine this ratio. So because we already know the rate constant, and we're asked to determine this ratio, we can use this equation. So this ratio, this equation, natural log of nt over n0, we're interested in calculating, is equal to negative times k, so negative times k times t, and we're told t is 100,000 years, or 1.0 times 10 to the 5th years. So we can solve for the right side of the equation. So natural log of this ratio is equal to negative times k times t, so negative 1.209 times 10 to the minus 4 times 1 times 10 to the 5 gives us a value of negative 12.09. So we can use the e to the negative 12.09, e to the natural log of this ratio. So then what we get is e to the natural log of this ratio, so e cancels out natural log, is equal to e to the negative 12.09. In other words, our ratio of nc over n0 is equal to e to the negative 12.09. So we have e to the negative 12.09 is equal to 5.62 times 10 to the minus 6. So that's a fractional ratio. And then to find percentage, of course, we'll multiply that by 100%. And when we do so that's in fraction, but in percent form, multiply by 100%, and we get a value of only about 5.62 times 10 to the minus 4%. So the idea is, and not only just an example of calculating this ratio if we know how old the object is alleged to be, but also to illustrate the point that, notice after 100,000 years, if this actually is 100,000 years old, how very, very little of the original carbon-14 would still be present, how very, very small this ratio actually is. And there are limits to how old of an object we can date with at least carbon-14. So the take-home message is that because carbon-14's half-life is only about 5,700 years, this carbon dating method is really only applicable, only good for objects that are certainly less than about 60,000 years old. Any more than that, and there's just so little carbon-14 present, not only are we estimating how much there was originally, but because there's such little of that carbon-14 left now, we also have quite a bit of uncertainty in how much there is now as well. So that gives our ratio has lots of uncertainty, so our age will also be very, very uncertain. So carbon-14 dating is, if it's older than 60,000 years old, if we think it's older than 60,000 years old, then carbon-14 would not be the best choice. We could use other radioisotopes that have longer half-lives perhaps, and certainly this carbon-14 is certainly better if we think the object is somewhere between 1,000 and 2,000 years old, because that's long enough time for there to be a difference between how much there was originally and how much there is now, but not so long that there's a huge difference between how much it was now versus how much there was originally. So with that, we finished our lecture material for chapter 21, which therefore finishes the lecture material for Chemistry 112 during the spring semester of 2020.